August 7th, 2025. The world held its breath as Hubble released data that shattered expectations. A razor-sharp image of 3I/Atlas, the rare interstellar comet blazing through our solar system at 210,000 kilometers per hour. This isn't another fleeting mystery. It's only the third time in history we've caught a visitor from another star on camera. The nucleus, far smaller than feared, yet still immense, trails a dust plume that matches our own comets, yet its origin is utterly alien. Scientists now scramble to explain what we've captured, with implications that could rewrite our understanding of how worlds form and die. So what did Hubble truly reveal about 3I/Atlas, and why did it make the world stop? Only 8 years ago, the idea of an interstellar visitor was pure speculation. Then, in October 2017, a telescope in Hawaii caught sight of an object streaking through the solar system on a path no comet or asteroid had ever traced. Dubbed Oumuamua, O-mu-a-mu-a, it arrived without warning, showed no coma or tail, and left scientists with more questions than answers. Its brightness changed erratically, hinting at a flattened, elongated shape, something never seen before. But what truly unsettled astronomers was its motion. Oumuamua accelerated as it left the sun, but there was no visible gas or dust to explain the push. Solar radiation pressure was considered, but the numbers did not quite add up. Some, like Avi Loeb at Harvard, even floated the possibility of artificial origin. Despite dozens of papers, the object was already gone. Too fast, too faint, impossible to chase. Just 2 years later, in August 2019, another interstellar traveler appeared. 2E Borisov was unmistakably a comet, with a bright coma, long tail, and a steady stream of gas and dust. Its chemistry, though, was not quite like any comet seen before. Spectra from telescopes in Spain and Hawaii revealed high levels of cyanide and carbon monoxide, and the dust grains were unusually small. Borisov's nucleus was also much more fragile, breaking apart as it neared the sun. Still, its overall behavior fit the playbook of solar system comets: active, icy, and volatile rich. For the first time, astronomers could compare an object from another star to the familiar comets of our own system. These two encounters changed the mindset of planetary scientists. Suddenly, interstellar objects were not once-in-a-lifetime flukes, but a new class of visitor. Detection networks like Atlas and Pan-STARRS began scanning the skies with new urgency. Protocols were rewritten. Time on the world's largest telescopes was set aside for the next alert. The lesson was clear. When a messenger from another star appears, the window to study it is brief, and every second counts. Now, with 3I/Atlas in our sights, the world is not caught off guard. The legacy of Oumuamua's mystery and Borisov's fleeting revelations has shaped a scientific community ready to act. This time, Hubble and its global partners are prepared to capture every detail, every spectrum, every clue. What we learn from this third visitor could finally answer questions left hanging since 2017, or open new mysteries altogether. As the data pours in, astronomers know that every observation is a chance to glimpse the birth and death of worlds far beyond our sun. If you want to see how these discoveries unfold in real time, hit subscribe. The story of 3I/Atlas is just beginning, and what comes next could redefine our place in the cosmos. On July 1st, 2025, the Atlas survey in Chile flagged an object moving faster than anything else in their nightly sweep. The first orbital solutions, calculated within hours of detection, showed a trajectory that was hyperbolic, an unmistakable sign that this was no ordinary comet. The team knew what that meant. The object was not bound to our sun. It was an interstellar visitor, only the third ever found. As the data streamed in, the urgency was palpable. Atlas team members sent out immediate alerts to observatories around the globe: Hawaii, Arizona, Chile, France. The message was clear. Point every available telescope at these coordinates now. The object was already racing through the inner solar system at nearly 210,000 kilometers per hour. At that speed, it would cross the distance from Earth to the Moon in less than 2 hours. There was no time to lose. Within 24 hours, the first ground-based follow-ups began. The Deep Random Survey in Chile and the Lowell Discovery Telescope in Arizona captured faint, diffuse light around the object. By the night of July 2nd, the Canada, France, Hawaii telescope reported a thin, hazy coma, a cloud of gas and dust that marks a true comet. This was the confirmation astronomers needed. The object was active, shedding material as it neared the Sun, not a bare asteroid like Oumuamua. The discovery was officially logged as C/2T25N1 Atlas, but the hyperbolic path meant it would soon earn the rare 3I designation for interstellar status. Every minute, new observations tightened the orbit. The Minor Planet Center began collecting dozens of astrometric positions from around the world. By the end of July 2nd, over 30 telescopes had contributed to the growing dataset, each one adding precision to the object's calculated path. The more data, the stronger the case for its interstellar origin. With the hyperbolic trajectory confirmed, the international community mobilized. Emails flew between comet specialists, planetary scientists, and telescope scheduling committees. The call went out for the most powerful instruments available. For the Atlas team, this was the moment their system was built for. Years of automation, rapid data processing, and global coordination paid off. They had caught the object early, much earlier than either Oumuamua or Borisov. The lesson from past encounters was clear: act fast, or miss the chance forever. As the first 48 hours closed, plans were already underway to secure time on the Hubble Space Telescope. The world's eyes were now locked on 3I/Atlas, with every observation a race against time. The next step would require Hubble's unmatched vision, and the clock was ticking. If you want to keep up with every new discovery as it happens, make sure you're subscribed. The story of 3I/Atlas is moving faster than anyone imagined. David Jewett knew the opportunity would never come again. Only 3 interstellar objects had ever crossed the solar system, and this one, 3I/Atlas, would be gone in weeks. He drafted the proposal himself, requesting directors' discretionary time on the Hubble Space Telescope. DDT is the astronomer's emergency switch, a way to bypass the usual year-long review cycle and seize rare, fleeting targets. Jewett's pitch was simple. No other instrument could match Hubble's sharpness, and no other moment would offer a closer look. The proposal landed on the director's desk at the Space Telescope Science Institute within days of discovery. Inside Hubble's operations center, the request set off a chain reaction. Schedulers pored over the existing queue, weighing the global impact of each planned observation. Competing projects, some in the making for months, were shuffled or postponed. The urgency was clear. Only a handful of events in Hubble's 35-year history had triggered such a rapid response: supernovae, gravitational wave afterglows, and now, a messenger from another star. By July 10th, the schedule had been rewritten. Jewett's team received the green light for a prime slot on July 21st, when 3I/Atlas would be 277 million miles from Earth and still bright enough for Hubble's cameras. The logistics were daunting. Hubble's instruments, designed to track slow-moving galaxies, had to be recalibrated to follow a comet racing through space at 210,000 kilometers per hour. Engineers uploaded new tracking commands, accounting for the object's shifting position down to the arcsecond. Every second of observation was precious. Jewett coordinated with ground-based teams to ensure that no data would be wasted. Calibrations, filter selections, and exposure times were all set in advance. The plan left no room for error. Directors' discretionary time is a finite resource, less than 10% of Hubble's annual hours. Each request is scrutinized for scientific value and urgency. For 3I/Atlas, the stakes were obvious. The last two interstellar visitors had slipped away with more questions than answers. This time, Jewett was determined not to let history repeat itself. His reputation as a pioneer in small-body astronomy carried weight. He had led Hubble campaigns for both Oumuamua and Borisov, earning the trust of colleagues and the respect of the committee. The approval set a precedent. Hubble's managers described the decision as a calculated risk, one that temporarily sidelined other international collaborations. But the chance to capture a visitor from another star system, with Hubble's unmatched clarity, was too rare to pass up. As the clock ticked down to the July 21st window, tension ran high. Jewett's team double-checked every setting, knowing that a single mistake could cost science its best look at an alien world. If you want to see how these once-in-a-lifetime discoveries are made, subscribe now. The next chapter will reveal what Hubble saw when it caught 3I/Atlas in its crosshairs. On August 7, 2025, the Hubble Space Telescope delivered what astronomers had been chasing for decades: the most detailed images ever taken of an interstellar comet. The data poured in, and for the first time, the core of 3I/Atlas, its nucleus, could be measured with real precision. Hubble's images set the size between 320 meters and 5.6 kilometers across. That range may sound broad, but in cosmic terms, it's a razor-sharp constraint. Even with Hubble's unmatched vision, the nucleus itself appeared as a point lost in the glare of its own coma. The solid heart of the comet could not be directly seen, but its presence was betrayed by the brightness and structure of the dust cloud surrounding it. The images revealed a living comet, a sunward plume, a trailing dust tail, and a coma glowing in reflected sunlight. Every detail matched what scientists expect from comets born in our own solar system. Yet this object arrived from the darkness between the stars. The dust loss rate, calculated from the brightness of the coma and the shape of the tail, matched fresh comets seen at similar distances from the Sun, about 6 to 60 kilograms of dust ejected every second. In other words, 3I/Atlas was behaving like it had always belonged here, even though its journey began in another star system. Hubble's sharp eyes picked out another surprise. Over the course of July, the coma's color shifted steadily redder. This subtle change hints at something happening near the comet's surface, a possible sign that solar heating was altering its composition or exposing new layers of dust and ice as it raced inward. The comet's speed, a breathtaking 210,000 kilometers per hour, left no doubt. This was a true interstellar visitor, moving too fast ever to be captured by the Sun. Spectral data from the James Webb Space Telescope soon joined the picture. Webb detected high levels of carbon dioxide, along with traces of water ice, carbon monoxide, carbonyl sulfide, cyanide, and atomic nickel. Some of these chemicals are familiar, seen in comets from our own backyard. Others, like the strong carbon dioxide signature, set 3I/Atlas apart. The combination of Hubble's images and Webb's spectra created a chemical fingerprint unique to this visitor. It is a blend of the known and the alien, a message in ice and dust from another world. Astronomers around the globe took note of the similarities and the differences. The dust plume, the tail, the evolving coma. These are the signatures of a comet shaped by solar heat and cosmic cold. Yet the exact mix of molecules and the way the coma changed color hinted at a history written far from our Sun. Each observation, each spectrum, brought new questions. Was 3I/Atlas forged in a planetary system like ours, or does its chemistry reveal secrets of a star we have never seen? The answers are still coming, but one thing is certain. For the first time, the world holds a detailed record of what an interstellar comet looks like up close. These findings are already fueling debates, inspiring new theories, and setting the stage for the next wave of discoveries. The story of 310I/Atlas is now a benchmark for science, a snapshot of a cosmic traveler caught in the act, carrying the chemistry of another star into our sky. Official recognition of 3I/Atlas was not automatic. As soon as the hyperbolic orbit became clear, astronomers worldwide began submitting astrometric measurements to the Minor Planet Center, the IAU's clearinghouse for small body discoveries. Each new data point tightened the calculated trajectory, but the debate over its status was fierce. Some argued that outgassing from the comet's surface could nudge the orbit, making a solar system object appear interstellar. Others pointed to the sheer speed, 210,000 kilometers per hour, and the sustained eccentricity well above 1, even after dozens of independent checks. By the first week of August, the Minor Planet Center had compiled 122 separate observations from 31 observatories. These included ground-based surveys in Hawaii, Chile, and France, as well as early Hubble and JWST imaging. The data were reviewed by orbital specialists who ran simulations to rule out every conceivable solar system origin. Only then did the MPC issue the formal circular. This was the third confirmed interstellar object, and its official designation would be 3Pi/Atlas. The process was not without tension. Some teams hesitated to share their measurements, hoping to secure discovery credit or first publication rights. Others pushed for immediate data release, arguing that the global significance of an interstellar visitor outweighed individual claims. In the end, the volume and transparency of the data forced consensus. The 3I designation joined a short, exclusive list: Oumuamua, Borisov, and now Atlas. Each one a cosmic messenger, each one a challenge to the boundaries of planetary science. Planetary defense agencies wasted no time running the numbers. With the comet's hyperbolic path and a minimum approach of 1.8 astronomical units, about 270 million kilometers, there was never any risk to Earth. NASA's Planetary Defense Coordination Office and the European Space Agency's NEO Coordination Center both issued public statements confirming a safe miss. Their simulation models, built on hundreds of independent observations, showed a trajectory that would keep 3I/Atlas well clear of our planet and even the orbits of Mars and Jupiter. For the global defense community, this was a rare live-fire drill, a chance to test protocols, communication, and rapid response analysis on an object moving faster than any comet ever tracked. The event also sparked new ideas. Some researchers are already sketching proposals for future missions: rapid launch probes, small CubeSats, even interceptor spacecraft that could be dispatched on short notice to meet the next interstellar visitor up close. While none of these projects are ready for 3I/Atlas itself, the urgency is clear. The lesson is simple: if we want to catch the next cosmic messenger, we need to be ready before it appears. The safe passage of 3I/Atlas is a reminder that our planet is not alone in the galaxy, but also not in immediate danger. The real opportunity is scientific. Each new interstellar object brings a chance to learn, to prepare, and to imagine what's possible. If you want to see where these discoveries could take us and how planetary defense is evolving, make sure you're subscribed and let us know in the comments, what should humanity do when the next interstellar traveler appears? On August 7th, 2025, Hubble released the sharpest images ever of 3I/Atlas, only the third interstellar object confirmed in human history. These data revealed a nucleus between 320 meters and 5.6 kilometers wide, traveling at 210,000 kilometers per hour, and actively shedding dust and gas across deep space. More than 122 separate observations helped confirm its interstellar origin, and orbital models from NASA and the European Space Agency proved a safe miss distance of 1.8 astronomical units. Yet, questions about its precise composition and the processes that shaped it remain open. Unlike past visitors, 3I/Atlas offered scientists a detailed early look, but some results, including full spectra, are still under review. The official 3I designation underscores how rare and significant these encounters are. As new data continues to emerge, one fact stands clear: 3I/Atlas has changed how we study visitors from beyond our solar system, setting a new standard for discovery and collaboration.